Thank you so much for joining us. This is our 97th virtual discussion, and today we're going to be talking about a really great, important topic, AV testing and simulation. So we all know the safe deployment of autonomous vehicles, it's going to require exhaustive testing. In fact, probably more than any product in history. We know that public confidence in AVs will be greater if people are aware of everything that goes into the testing of the technology. So we have a couple of really great panelists here today to help us walk us through how testing and simulation works. We have Sunmin Kim, Director of Public Policy at Applied Intuition, and Tim Dawkins, Senior Technical Director at Einride. Sunmin, Tim, thank you both so much for being here today.
Thanks for having us.
Excellent. So just starting off really broadly, can you both tell us a little bit about how your companies support AVs through testing and simulation? Sunmin, you want to start?
Sure. So I'm from Applied Intuition. We're a late-stage startup. We've been around for about 5-6 years now, and we're primarily a tooling company. So our customers, which include anywhere from the large auto OEMs to some of the top AV startups, like Einride, use us throughout their whole development cycle, all the way from doing object or sensor level simulation to using our tools to actually log and manage that data, to all the way to verification and validation, where they're going to be looking at how all of these virtual tests are tied to the requirements that they want to be testing for. So we are based in Silicon Valley. We're headquartered in Mountain View. I'm personally based in Washington, D.C., and then we have 6 other offices worldwide.
Great.
And so to pick up from that, so as Sunmin said, Einride is a full stack autonomous vehicle developer. So not only do we develop our own automated driving software, but we also develop our own vehicles too. So you can see behind me the Einride trailer, and we have our pod, which is our box truck. So we developed the whole thing from the chassis up the body, as well as the sensors and the software to drive the vehicle. So naturally, testing is a huge part of all that we do. We're doing it constantly on new software releases, new hardware, and new vehicle platforms, and tools like Applied's simulation environments, Simian in particular, are an essential part of the bread and butter of enabling us to do what we do. So really looking forward to getting into today's discussion and unpacking that a little bit more for this audience.
Awesome. Well, I love that we have both sides of the equations here. So so thank you both for being here with us today. I'm looking forward to this conversation. I'm going to go ahead and give a shout out to Applied Intuition's validation. Sunmin, can you talk a little bit about what verification and validation is, and sort of what services Applied Intuition offers in that realm?
Yeah. So verification validation is a structured way to test whether and verify whether an autonomous system meets the requirements you want it to. So if you want to sort of unpack the word verification versus validation, verification is essentially, have I done things right? So assuming that this is the right system that you are designing, is the system operating in the way that I designed it? And then essentially validation is, have I actually done the right thing? So did I actually design the right system? And the way that we support verification validation, our set of best practices are really relied on system engineering principles, but starting all the way from the design of the system to continuous validation, verification, continuous testing, all the way to what are the requirements that we're looking for. I think the interesting thing about verification validation too is, if you ask an engineer how a system should behave, that might be slightly different from how a government regulator in the transportation sector might be looking for. So an engineer may be thinking, well, we want this vehicle to be able to apply this amount of force, or be able to not slow down as much in this kind of curvature, while for a government regulator, they're more looking for, we want to make sure that you're driving within the speed limit, don't hit other cars, and more sort of performance-based metrics. So verification and validation provides that bridge between the technical engineering requirements to the actual performance requirements. And the way that Applied tools sort of fit into it, so I mentioned that we have a suite of products starting all the way from the actual simulators itself to our product called Basis, which essentially helps you manage all the tests that you've been running and then be able to say whether those requirements were met. So many of our customers sort of can pick from our menu of options when it comes to tools. They don't have to necessarily use our own simulators. They can use their own simulator, but also use Basis to actually do verification and validation. But essentially, ideally, you're using our simulators from the start, and then all the way to Basis to actually do VMV of their systems.
Excellent. And I do want to say again, for anybody who's interested in this subject, it is a really great handbook that breaks down, a lot of the key points you just made. And I recommend anybody who's interested in this to check it out. It's a great handbook, and a great job to your team for putting it together. So Tim, just from your side, how will better testing for AVs allow the industry to scale up their deployments in the future?
Well, as I said at the intro, testing is everything for our company. And if autonomous vehicles are to succeed and to scale, we have to prove everywhere we deploy them that they are acceptably safe. And for us, that means building a strong safety case that captures a holistic analysis of everything that we do, from development, design, manufacturing, all the way through deployment, how the vehicle operates whilst it's in use, and then also at the end of the life cycle, when the vehicle's being retired. So we have to think holistically about the safety of that vehicle throughout that entire period. And we follow a number of industry standards throughout that process. And testing effectively is the evidence that we rely on for a lot of the practical aspects of how the system works, and enables us to prove, to verify that the design intent for the vehicle is met and is satisfied throughout operation, and that we can stress test it against things that we're likely to encounter as well when we're operating on the road. And so we need various tools and environments to do this. Simulation is a huge part of it. We also use, right at the kind of initial software phase, a series of kind of software QA tools and, peer reviews, etc. And then, that's probably when the simulation starts to pick up in earnest, when we start doing so-called software in the loop testing, where we kind of simulate the vehicle being used on the road. We also do hardware in the loop testing, where we have basically the vehicle's brain and sensors stuck on a bench so that we can load it up onto that without actually needing to load it onto a whole vehicle first. Then at some point after that, we'll take it to the test track and test some slightly more dynamic aspects of the vehicle, let's say, in a controlled environment. And a big part of that aspect is also verifying that our simulation models accurately match how the vehicle performs in the real world. And then after that's all done, and if we've gotten green lights across the board, then we'll think about putting the vehicle on the road and verifying how it performs in the places that we're going to be using it, and testing things like its localization in the real world. Wow, so obviously better tooling to be able to replicate the environments that we're going to be deploying in is key, because the more accuracy we can bring to those early stages, the more time and money it saves us, and also the safer our products will be.
It's amazing. I really think a lot of people out there in the public don't realize the variety, depth, and breadth of all the testing that goes on when it comes to AVs. And kind of in that line, I'm going to give you a follow-up question here. Can you give us some insights into, you talked a lot about the different methodologies of testing and simulation and things. How rigorous is it before the vehicles ever hit the road when it comes to AV testing technology?
Yeah, so we're very methodical, and I'm going to describe an approach which might seem kind of slow and hard to scale, but it's the reality of how our trucks come to the real world. So for us, it starts with the operating domain, or the operational design domain, or ODD. And for us, we make an electric Class 8 truck, a box truck, and the tractor trailer that you see behind me. So this is intended to drive from, say, a manufacturing plant to a distribution warehouse, and to do repeatable runs over and over again. That's fundamentally the use case for the trucks that we have today. So this means that when we're looking at deploying in a new place, say it's a new customer, a site that we want to test, then we'll say, all right, we're starting here and we're ending here, and we're following exactly this route. So unlike, say, a robo-taxi, which might have to pick up a customer in one part of the city and drop them off in another way and could get there a dozen different ways, we're able to start by evaluating our route and saying we're only ever going to follow these roads and we're going to follow, go through these intersections, and it really narrows down the number of unknowns that we're going to be encountering, essentially. So that basically comprises our initial feasibility evaluation of a deployment, where we look at the road type, the environmental conditions, the weather, the time of day, etc., the traffic, and we assess that against the capability of our software today, or perhaps our future planned releases. And from there, that's when we start going, okay, how do we simulate this to kind of test our hypotheses that we can operate safely here before a deployment? So we'll create a simulation model and start running scenarios day and night, pretty much around the clock, to simulate how the automated driving system will work on that route from the very beginning. So this is a very hours and mileage intensive process, but it's all done in the cloud, at least. And then we'll start introducing scenarios and start kind of ramping up the difficulty and complexity to see at what point we kind of reach the limits of our capability. Now, separately from that, this is assuming that the software, we're using an existing software release. If we're using a new software release, then that in turn needs to be further validated. So say we've developed a new software version, or we've changed some features or fixed some bugs, then that will have to kind of restart that QA release and review process, that software in the loop, hardware in the loop, track testing, etc. And then we have a series of acceptance tests that when the software gets pushed to the vehicle, it goes through as well to make sure that everything's actuating correctly and the localization works as it should, etc. So all of this sprawling mess is our comes together in our safety approval and release process, which is actually a very structured gating process that looks instrumentally from the very beginning. Is this something we can do, all the way through to how will our vehicle perform when it gets to the site, with a series of metrics and acceptance criteria tied to each approval along the way. So suffice to say, our testing, verification, validation team are very, very busy here at Einride.
Well, it may be sprawling, but that makes sense. It ties into what you were talking about earlier with that safety case. I mean, there's so much that goes into it. And I also like the point you brought up about how the environment for AV, it's not all the same. Whereas if you're on sort of that middle mile route, it's, there's it's a lot less dynamic. There are fewer unknowns, and that plays into some of the ways that you can get on the road and things of that nature. So very interesting. So Sunmin, can you describe what we mean when we talk about edge case? Because an edge case is one of those terms that may not be familiar with the wider public when they're sort of considering autonomous vehicles, and how does that sort of tie into testing and simulation?
Yeah, so the way that we think about edge cases sort of twofold, that there are cases that could happen in the real world and sometimes do happen in the real world that are both expensive and unsafe. So one example of trying to replicate an extensive edge case is you may be driving behind a truck and then there's a 6-foot ladder that falls out of it. How will the AV actually react to that? That's very expensive to actually try to do real world testing. You're probably going to crash your car and there's a truck involved and there's a 6-foot ladder involved. So those kind of things may be better to do it in a simulated environment. And then if it turns out to be that that's a really important edge case where the AV or the AV stack is really struggling with it, then you might want to actually invest the money to do real world testing. Or like an example of something that is unsafe is like if you're responding to emergency vehicles that you weren't really predicting, that was not a normal route that an emergency vehicle might go on. That's very unsafe to sort of test out. And then also like there's weather patterns. Let's say it's been a rainy day and there's a sudden break in the cloud, so everything is very reflective. It's very unsafe to test on in the real world. So that's really where simulation comes in. The fact that you can actually simulate those into digital environments. And I think that the technology has gotten a lot better for that. And I think the technology is also catching up to this as the sensors have gotten better for that. The AV is also able to, for better, for worse, to detect all of these different environmental conditions that may affect how the AV actually responds. And then the last thing I'll mention here is that, I think there's also sort of dangers of over relying on human generated conditions or those edge cases. If you think about how we drive normal vehicles, we have decades of experience of like what we consider those to be edge cases. So like the weather example is a perfect one, because anyone who has driven in bad weather, like they know that that's the edge case that may be a little bit dangerous. But for an AV, or how a computer may think are the edge cases or the things that are hard to predict, I think we have to be cognizant of the fact that, like, that might not be the typical edge cases that we're thinking of. And that's because AVs have, multiple failure modes. I think when we're talking about conventional cars, we're really thinking about how the mechanics or the physical parts really fail in certain conditions. But when you're talking about an AV, we're really talking about how a software may fail in certain conditions. And that's sort of where, simulation becomes increasingly important. So you're able to test a whole variety of different cases to find what are the edge cases that may be unique for an AV versus a conventional vehicle.
I think I'd like to put a finer example on that. So Sunmin gave us a great example at the beginning of like a ladder falling off of a truck, which, yeah, when you and I think about driving, this is something that happens maybe you might experience that once every 100,000 miles. But sometimes some of the things that might trip up an automated driving stack would be, say, a combination of actually quite ordinary variables that come together in an extremely rare circumstance. So it might be a specific combination of, say, cars parked on either side of the road and a pedestrian crossing and the sun being at a low angle. Those individually may not be a showstopper, but if those suddenly came together in the perfect set of parameters, it might result in a fatality if your perception system doesn't solve and perceive the environment correctly. So what simulation tools enable us to do is not only to create some of the abstract scenarios that we can think about and think about random objects appearing in the road or extreme environmental conditions, but to combine routine scenarios with very large amounts of variation in those variables, and to repeat those with tiny little changes over and over and over again to see if we can really find the true performance, and to solve for those kind of improbable but frequent combinations of events which might trip us up.
Yeah, I think that's a really good point too, because I know that my mind always goes to, when I think of an edge case, it's something that's a very unique or very rare situation, but just combinations of things can make it something that has to be modeled and prepared for AVs. It doesn't have to be something completely out of left field. So that's a really good point. And sort of staying with this theme of the technology in the real world, Tim, how does the simulation technology from your side model the real world?
Yeah, so if we come back to my example of how we kind of go through our deployment process, we always start with a specific route in mind. So a flow, we call it, because we're moving goods from one place to another. And so when we start to model the real world, we build a model of that route. So this starts at an abstract level with pulling up a map of it and then building that same environment in Simian, which enables us to basically recreate those roads, those intersections, and the geometry, and then start to populate it with the traffic signs and inject traffic, vulnerable road users, and other things that we're likely to encounter. And also, not to overlook, we also have to put in the geography itself, so hills and the kind of environmental factors that we're going to encounter, the place that we're going to be deploying our truck. And then most of what we use that model for is what's called object level simulation. So this is to recreate behaviors and traffic interactions of, say, encountering other vehicles or, as I said, vulnerable road users. And this enables us to construct scenarios where we're combining say interactions with those road users and anticipating, say, what happens if someone runs a red light, or the hazardous things that we think we might encounter when we're on the road here. And as I mentioned in the previous question, we then start to fuzz those variables basically to create thousands of different combinations of interactions with slightly different parameters in order to really increase our coverage and give us, you know, many tests and repeatable results that we can say, okay, we've got some confidence that this is going to work.
Well, that sort of leads into my next question for both of you, really. And I think it's an interesting one that's on a lot of people's minds. Where does simulation and real world testing begin in terms of how companies make that determination? Sunmin, can you speak to that first?
Yeah, I will sort of give a cop-out answer, which is like there's no sort of clear line where
Right.
one ends and one begins. So if you look at the traditional approach of, I think, safety testing, like it's sort of like the waterfall method of you're dealing with very interpretable systems. So like, let's say you're talking about brakes. So for a safety engineer who's going to be testing those brakes, your variables may be just the amount of force in certain nominal conditions, and then there are very structured ways to sort of monitor and interpret the results that you get. And you also know how to measure those results you get. So like the result may be, the deceleration rate, or it could be just like how fast you were able to come to a complete stop. But if you're thinking of autonomous functions, you're having to react to a much more diverse set of conditions. So you're way more likely to encounter something that you didn't expect. So when you're testing something like a brake, you have the set number of variables, and then you can sort of backfill that testing. And then at the end of the day, or maybe not day, but like weeks or months, you can have a pretty high confidence that you were able to backfill something that a specific variable or a specific condition that you needed a higher level of confidence for you to get the requirement that you wanted. But with autonomous functions, because you're way more likely to encounter something that you don't expect, you got to keep going back and forth, which is why I say, I don't think there's a line where the real world testing begins or ends and then a simulated testing environment. So most of our customers actually, sort of random, and we have products that support, you're logging real world data, and you saw that the vehicle that you were testing didn't perform very well, but you're not sure what made that not perform very well. So in our tools, you can tweak different conditions and find what of those conditions made the vehicle not perform well, and then you can sort of take it back into real world testing to make sure that that was a variable that was causing the software problems.
I can give you a very specific example where we use both physical testing and simulation-based testing to solve for a new feature effectively. So we recently deployed our truck on a new route with a customer which had a 15% gradient on it. And suffice to say, if you're trying to do that in your head, that's a very steep hill, especially if you're in a big Class 8 truck with several tons of goods on board. So in order to this is the steepest hill that we'd driven this truck up. And before we could get to the site, we had to make sure that our hill hold feature, in the event that we had to stop on this hill, would be able to safely stop the vehicle and then reinitiate it again by gently feeding in power and getting it underway without slipping the tires and, otherwise losing control. So this sounds very mundane, but it was when we looked at this deployment, this was one of the things that jumped out at us as a new problem that we had to solve. So what we did using our simulation model is we, as I said, recreated that environment. This is why I mentioned the geography and the hills. And we accurately created that simulation that allowed us to tune and model the various scenarios under which we would stop on the hill and the amount at which we should be reapplying the throttle and releasing the brake at the same time in order to kind of initially set up this hill hold feature. Obviously, we needed to verify that this works in the real world as well. But the hill itself isn't a constant 15% gradient. So the simulation model, we were able to tune some of the parameters and to say, all right, well, what if it was 18% here? What if it was 10% here? What if we go 10 into 18? We can kind of change the profile of the hill almost infinitely. But that still didn't negate the fact that we had to go to a test track with a steep grade up in Michigan and put some stuff in the truck, wet the tires, and see at what point that we had too much acceleration applied and too much slip. So this is a very tangible example of where we needed to kind of calibrate this specific powertrain control feature. And simulation was very, very useful in terms of us setting up the behavior. And then we used a track environment to verify that we had, with one set of quite extreme parameters, that we still had a safe system.
Sounds like the better way to think about it. Instead of a linear testing, process with benchmarks at specific times, it's more of a testing ecosystem that everything plays in to everything else, and it's much more organic than just a strict decision on when to do one or the other. So I'm glad you both gave us that insight. Tim, you all at Einride have a really interesting, or a sort of unique model for deployment. Can you talk a little bit about how remote operations versus traditional AV impacts testing prior to deployment?
Yeah, so at Einride, we develop cabless, uncrewed vehicles. So there's no place for a human in our trucks ever. From day one, we've never put people inside one of our autonomous vehicles. And so we've relied on remote operators to supervise our automated driving systems in operation. Now, I want to clarify that our remote operators do not carry out the dynamic driving task of the truck when it's on the public road. Their primary job is to ensure, whilst the truck is operating, through video and sensor feeds that they have at their bespoke remote operations station, their primary job is to make sure that the ODD conditions are satisfied whilst we're operating. So the the weather hasn't suddenly changed, and we're not encountering something that is outside of our operating design domain. And in the event that that's no longer the case, they're there to manage the transition to a safely out of that ODD. So say to bring the truck to a safe stop or get it to the side of the road if needed. Now, practically, coming back to your question about testing, our remote operators are very heavily involved in our testing process. So whenever we are at a test track, all the way through to our on-site acceptance tests, we use the same remote operators so that they develop a very intimate understanding of how the vehicle behaves, what happens when it encounters a hazardous scenario, because they've seen it, they've tested it, they've done it. And getting their feedback through the testing process is just as important to us as an indicator of our readiness as anything else, frankly, throughout our process. I should add that all of our remote pod operators, or RPOs, are professional truck drivers. They all hold Class 8 CDLs, and we have a good handful of them here in the US. 50% of them are Teamsters as well, so we're not eliminating union trucking jobs, actually, far from it. And so we're very much committed to keeping a remote operator as part of our solution, and we see them being a part of our solution for the long term.
That's so great. I think a lot of people would be interested in that, when people think of AV, and we've had discussions on this before in the past, or any types of these advanced driving solutions, they don't realize that there's also an opportunity for a future type of workforce, and Teamsters and folks that are evolving along with this industry still have a place. So I think that that's a great point that you just made.
Yeah. Rely a lot on their expertise of, having driven large trucks in the real world to help us understand what safe behavior is for these vehicles.
That's great. That's great to know that they're giving you feedback and providing that input. That's really cool. Sunmin, do you see AV testing and simulation evolving in the future as more vehicles are deployed, more companies into the space, things like that?
Yeah, so two things here. One is, and I'm a little biased because we are a tools company, but I think the tools have actually gotten a lot better in the past 5 to 10 years. I think the biggest difference is the fact that they're a lot more scalable. So now we have tools that are able to do that are able to run in the cloud. We have tools that aren't just simulating as an object, but rather actually taking the sensor data. And I think you're going to see more tools be available in the marketplace, as well as they're going to be even more scalable. And then the second part of this is we're starting to see regulators worldwide adopt virtual testing tools. And I think this is sort of in line with regulators testing for crash avoidance, not just crash worthiness. And for something like crash avoidance, you need to rely more on simulation and virtual testing so that you can test for all of these edge cases that I talked about. But that's definitely something that we are like very passionate about. The fact that we're able to give those tools to government safety test officials so that they're able to use virtual testing methods as they're trying to do verification and validation of AVs.
So I feel like I say this every time, but I wish we had a lot more time with both of you because this is a fascinating discussion. Unfortunately, we are running out of time today, but I did want to mention, Tim, I wanted to congratulate Einride for your recent approval on opening up U.S. operations. So that's very exciting. And to all of our viewers, I know we try to get to some of these viewer questions sometimes we're able to, sometimes we're not, but they are not lost. We do keep them and put them out there for our experts to answer in the future. So I just want to say thank you to both of our panelists, Tim, Sunmin. We really appreciate you both being here and giving us all these great insights. So I really appreciate it. Once again, also to our audience, thank you for spending part of your day with us. You can find this and a lot of other great resources on our website, pavecampaign.org. We also have our podcast. We just did a great episode with Applied Intuition, by the way, on the verification and validation handbook. So check that out. And once again, just thank you all for spending part of your day with us.
Thanks for having us.
Yes, thanks for hosting this great discussion.